Hello everybody, in this lecture we will be solving 1992 IMO problem number 6. Here is a view of this problem. For each positive integer n, let s of n be defined to be the greatest integer such that for every single positive integer k less than or equal to s of n squared can be written as the sum of k positive squares. So we need to first prove that s of n is less than or equal to n squared minus 14 for each n greater than or equal to 4. So let's start with the smallest of those n's just to make sense of what's going on. Let's consider the case n is equal to 4. Then 4 squared. So we can definitely write it by using the sum of one positive square, which is just 4 squared. But 4 squared is 16, and alternatively, this is the least, the most efficient way of writing it. The least efficient way would be to write it as 1 squared plus 1 squared all the way up to 1 squared, and using 16 of them. Here we have made use of, here k is equal to 1, here k is equal to 16. Now what is s of 4? Let's keep trying. So how else can I write this 16 here? Well, we can get rid of some of the 1 squares, right? For instance, with a 2 square, so I can still keep a bunch of 1 squares. How many of them? 12 of them. And then I can add a 2 square, right? So as a result, we have 12 of them here plus another one here. So for a total of k is equal to 13. What else can I do? Well, I can write it in terms of 2 squares. So 1 square plus 1 square plus 1 square plus 2 square plus 2 square. So 2 square plus 2 square is 8. So we have 2 terms here, and in order to get an 8, we need to have 8 more terms here. So therefore, the total here, k is equal to 12. So just as a quick note, look at the number of the sum of the k squares here. So k was 16 here when it was all ones, and when I replaced a bunch of ones with just a single 2, a 2 square, because 2 square is 4, it's 3 more than 1 square. I got rid of 4 1 squares and replaced it with a single 2 square, so the difference has been 3. So I have written it more efficiently with 3 less terms. So that's why k went down to 3. And when I introduce a second 2 squared, k went down further. So in fact, applying this procedure, it is obvious that if I keep applying this, so I have 1 square plus 1 square plus 2 square plus 2 square. When I introduce the third 2 square, I will get 4 plus 4, 12. So I have 4 remaining 1 square. So we have 4 of them here, 3 squares here, 3, for a total of k equals 7. Now the optimum would be when in fact, okay, so this case has been very interesting to me. Let's finish up this whole calculation. So, and then there is 4 1 squares here. We can just replace them with a single 2 square. So now we have 4 squares here. So therefore k went down to 4. So still I'm not done. There's a couple things I can do. For instance, I have never used a 3 square. What happens when I introduce a 3 square? When a 3 square is introduced, so in fact, as a convention, we can even do from the largest to the smallest. So let's introduce a single 3 square. So this is equal to 9, plus I will have 7 more 1 squares. So there's a single one here, 7 more here, and 9 plus 7 is 16. So k here is equal to 8, and this is not in the list. That's good. What else can I do? I can have 3 square, and then maybe a 2 square. So 9 plus 4 is 13, and then I have 3 more 1 squares. So therefore, in this case, k would be equal to 5. And let's keep going like this. What else can I do? Unfortunately, I don't have enough 1 squares to replace it with such that I get an additional 2 square or 3 square. But I can have this one, 3 square plus 3 square, So that would be oh no, that won't work actually, right? Because 9 plus 9 is, yeah, that won't work. I guess that's it then. Is there anything else I can do? I can't see any other thing. So therefore, finally, when we collect all these k's together, we realize that we have a solution for k equals 1. Then the least one is 4, 5, 7. 4, 5, 7, 8, 10, 13, 16. 8, 10, 13, and 16. We will always have a 1 and a 16 for sure. So this is just n squared, which is in our case 4 squared, and this one is just 1 squared, so that's good. So what is S of n then? S of n was, by definition, recall what S of n is. S of n is the greatest integer such that for every k less than it, n squared can be written as the sum of k positive squares. So yes, in that case, in this particular case, S of n is 1 because, well, 4 works, but 2 and 3 doesn't work. And so we need to find the greatest one for which anything smaller should work, and there's only one, and it is S of 1 is therefore equal to S of, sorry for that, not S of 1, S of 4. S of 4 as a result is equal to 1. If we can obviously do similar calculations for 5 and so on, right? But then let's go back to our original problem. So for n greater than or equal to 4, this thing should hold, right? So what this tells me, this is kind of like, there are two ways I can do. Either I can prove that it works for all the numbers up to n squared minus 14, whenever n is greater than or equal to 4. And by the way, in our case, we got that, recall that we got S of 4 is equal to 1, and obviously 1 is less than or equal to 4 squared minus 14, which is 2. It is not quite exactly equal to 4 squared minus 14. That's the second part of the problem. We will be looking for conditions when that will be exactly equal to. In our case, S of 4 got simply equal to, because it's equal to 1, it is simply equal to 4 squared minus 15, not 14. So that's crucial. So in a similar way, we can calculate S of 5 and the others, but we will do it in the second part. Now that we have a main idea what's going on, let's attempt the first part. So part A. So we need to prove that S of n must be less than or equal to n squared, has to be less than or equal to n squared minus 14. So let's generalize this thing. So we have an n squared, and the worst thing we can do, the least efficient way, would be to write 1 square n squared times. So we have n squared of these. So k here is equal to n squared. And then what I can do efficiently is, so what I need to do is to try to get, I want to see if I can get k equals n squared minus, for instance, 13. If I can't, then it proves that S of n would be less than or equal to n squared minus 14, right? So therefore all I will do is claim k equals n squared minus 13, not impossible. And I understand here my notation is very sloppy, but okay, so that's fine. All right, so if we start from k equals n squared for this term here, n squared, what's next? Oops, sorry for that. What's next? Well, one thing I can do, like the procedure I applied for the case n is equal to 4, I can remove some of the 1 square with the 2 squares. So 1 square, if I remove 4 of them and replace it with a single 2 square, so here I would get k is equal to n squared minus 3 versus here, n squared minus 4, my apologies. Here k is equal to 1, well, not k, but you get the idea. For a total k is equal to n squared minus 3. So that there's no confusion, let me just write the count here. n square minus 4, and then 1 here, plus 1. So we have n square minus 3. And can we ever reach n square minus 13 with this procedure? Well, because like we did here, right? So I can only use 2s and 3s. If I use a 4, it becomes too big. So do you see that? For instance, if I replace some of the 1 squares or 2 squares with a 4 square already eliminates at least 16 ones, and that's not good because it's already n square minus 15. It's already too little, right? Too less. So I'm only allowed to use 2 squares and 3 squares. But notice that each time I use a 2 square, I'm eliminating 4 ones and replacing it with 1 2 square. So therefore the differential between consecutive terms is 3. So I make jumps of 3. Jump by 3 when replacing 1 squares with a single 2 square. Right? So does that make sense? And in a similar way, like we did here, observed here that, for instance, I used to have 16k, k used to be 16, and by just introducing a single 3 square, the value of k went down by 8. Do you see that? Because 3 square is equal to 9, which is 9 1 square. So I had to remove 9 1 squares and replace it with a single 3 square for a difference of 8. So when I apply this procedure, so replacing the 1 squares with either 2 squares or 3 squares, and so I will jump by, in this case minus 3 obviously, by minus 8 when replacing 2 squares, when I replace 1 squares with a single 3 square, and to be more exact, when replacing when I replace 9 1 squares with a single 3 square, and here when replacing 4 1 squares with a single 2 square, right? Does that make sense? So therefore the problem is reduced to the following. By using 3 and 8, can I find the combination where I can get a 13, right? So is it possible to solve this linear equation is equal to 13? And the answer is no, at least no in the positive integers, I should say, with where x and y are positive integers. Well, obviously if I introduce negative numbers, of course it is possible to get a 13, because the greatest common divisor of 3 and 8 is 1, and I can get, yeah, I can reach to anything, right? Any multiple of 1 is reachable, but not when you are restricted to just positive numbers. In fact, let me even write down all the numbers that one can reach. So we can use, so what can we use for x and y, and which values can be reached here? So it's not too big, but let's just do it for the sake of completeness. So if I use 1x, 0y, we will get a 3. If I use 2x, 0y, I will get a 6. I use 3x, 0y, I will get a 9. 4x, 0y, I will get a 12. 5x, 0y, I will get a 15. And I already passed it, so this one is way too high. Okay, how about I use, this time I use no x, 1y, I will get an 8. 1x, 1y, I will get an 11. And 2x, 1y, I will get 8 plus 6 is 14. Oh, I already passed it, and that's it. Those are all the numbers that I can achieve. So 3, 6, 9, 12, 8, and 11. That's it. And in fact, these numbers should be matching with these numbers here, right? So the numbers that I have used here, for instance, here the difference is minus 3. The difference here is minus 6. And so pretty much these numbers here, 3, 6, 9, 12. The next one would be 9. Well, 12 in this case, but 9 should be somewhere here, for instance. That's 11. And which one is 9? Wait a second. 9. If I remove 3. Oh, of course, this one. Sorry for that. I missed it. This guy here. Okay. So, but I guess everything is clear here. I don't want to introduce too much formalism, but it's possible to express everything here in a formal way. Now let's go back to the second part of the problem. So part B. So when will S of n be exactly equal to n squared minus 14? Because in the case of S of 4, we realized it's not equal to n squared minus 14, but rather n squared minus 15. It turns out that after you do some trials and errors with the Pythagorean triples, probably you realize that well, yeah, so it turns out that 13 is the magical number, right? So because 13 square, so 169, I claim is the magical number. Obviously, when you do a few trials, you immediately realize the power of this. So you can use k equals 1 here, and then 169, you can split it as 12 square, 144 plus 5 square. But then 5 square can be further split, right? 5, 12, 13 being a Pythagorean triple, obviously, everybody knows that. So, and then 12 square plus 4 square plus 3 square. Oh, so now we are using 3 terms. And then for the 4 terms, yeah. 11 square, which is 121. So 169 minus 121 is 48. And then 4 square, 4 square, 4 square. So it's almost magic. And finally, for 5 terms, let's do one more. For 5 terms, I think 6 square plus 6 square plus 6 square plus 6 square plus and 36 would give you the 144, and then we can introduce back the 5 square, and then we can go on in this fashion. For instance, we can even find 6, and 6 would be just splitting this into 2, and so on. So that's very efficient. So what we are doing, so far we did show that this works for k equals 1, so S of n is at least, S of 13 is at least 1. Now it works for both 1 and 2. That's pretty good. So S of n so far is, S of 13 so far at least 2, but now it works for k equals 3, so S of 13 is at least 3, and so on. K equals 4, 5. So this looks really promising, but will it actually work? The answer lies on what we did here on this procedure that we have implemented so far. In fact, I claim that for all the numbers, actually, let me create the following claim. I would not prove it, but the proof goes along the same logic here, like the table that we created. You can create a similar table and check it for yourself. But I claim that if you have n and k as integers, right? If you have integers, satisfy 15 less than or equal to n, which is less than or equal to 4k, and secondly, let me write down like this. So these two inequalities, n minus 14, if these two are satisfied by n and k, then n can be written, in our case n is equal to 169, obviously, and can be written as the sum, or you can think of n as n squared, obviously. Okay, as the sum of squares of k numbers, each of which is equal to 1 or 2 or 3. So this is even stronger than, so we don't even have to bother trying a lot of things, but we can just focus our attention on 1, 2s, and 3s, like I did here. For instance, I just focused my attention on what happens when I use 2s and 3s here, and combination with 1, obviously, with a bunch of 1s. It turns out that this already eliminates a lot of things. It already checks on a lot of things. For instance, in our particular case, n is equal to 169. So if when I'll leave it to you to prove it, because I am already way over time. But the main idea is you can just check it, for instance, in mod 3, and it's not too hard to find the 3 solutions. Do I have time? Okay, let me at least write down the proof sketch. So the proof. Okay, so proof. Oh my god. Okay, so proof. Just a sketch. So I claim that well, the claim of this, what this claim is telling us is that x plus y plus z, the number of 1s, 2s, and 3s combined, should be equal to k, and then, well, where x is the number of 3 squares, y is number of 2 squares, and z is number of 1 squares, and second of all, 9x plus 4y, 3 squared x plus 2 squared y plus z, 1 squared z, must be equal to n. And we are looking for the solutions in non-negative integers, right? X, y, z are non-negative integer solutions to this system, and we claim that, of course, this system has non-negative integer solutions, and I leave it to you to check it. So I claim that this provides such a solution. So 2, so this is equal to 2 if n minus k is congruent to 1 in mod 3. It's equal to 1 if n minus k is congruent to 2 mod 3. And finally 0 if n minus k is congruent to 0 mod 3. Okay, that's for y. Once you know, so for x, once you know the x, y comes out like this: n minus k minus 8x over 3. Don't worry, the way we defined it as a piecewise equation will ensure that y would be an integer as well, but you need to check it for yourself. And z is equal to k, once you know x and y, obviously, because z should satisfy this, x minus y. So I claim that this holds, and I'll leave it to you to check that these three, the way x, y, z defined like this, satisfy both of these equations. The first one is trivial, the second one requires a little bit more work, but make sure that you also make use of these conditions when you do your solution, right? Okay, so let's go back to using this for in the case of 169. So in our case, n is equal to 169. So it's between 15 and obviously 4 times what's that? 172 is divisible by 4, so 86, 43. Yeah, 43. So therefore, this implies that if this claim and its proof is true, which so you will confirm it later on. So this thing will work for any k less than or equal to n minus 14, which is 155. And by the way, this n minus 14 is our guy, right? So it is our thing. Okay, so but that's really powerful. So what it is telling me, I don't have to worry for any k, so because k we realize should be at least 43. So for any k between 43, 44, all up to 155, there is no gap. So that's perfect. So we can always find the sum of 43 squares, or the sum of 44 squares, a sum of 155 squares, which will give us 169. Now, what do? I think at the beginning I already proved it for k equals 1, 2, 3, 4, 5. So what do we do for the numbers for the case between 6 and all the way to 42? So we are still missing those. So we need to handle those. But these are also pretty easy. Noticing that, consider, for instance, So for instance, I know that 169, if you look at the last one here, let me continue here actually. 169 is equal to 4 6 squares plus a single 5 square. So I can further split 6 square as a sum of a bunch of things, right? So using this same lemma. So if I apply this claim again for the case of 36, so I realize that 36 is between 15 and so this is 4 times 9. So the least value that k should be is at least a 9. And then according to the second inequality, it is 36 minus 14, 22. So therefore, it's possible to represent 36 as a sum of squares for any k between 9 and 22. If we also try it for smaller k's, let's say 6 square, what else can I write? So I can write it as a sum of 3 squares. So 36 is just 16 plus 16 plus 4, so it is just 4 square plus 4 square plus 2 square. So it works for k equals 1, it works for k equals 3, it doesn't work for k equals to 2, by the way. then it definitely works for 4, right? So why? Because it's 3 squared plus 3 squared plus 3 squared plus 3 squared. The rest is just number sense. So it works for k is equal to 4. It works for k is equal to 5 as well. 4 squared plus 3 squared plus 3 squared plus 1 squared plus 1 squared. What else? It works for, so this is 3, 4, 5, 6. It should work for 6 as well. 36, 16, 4, 4, 4, 4. Yeah. So therefore, 4 squared plus 2 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 squared. Yeah, it definitely works for 6 as well. It will work for 7 as well. So, well, you can check that it will work for all the numbers up to 8, right? So this is very easy. So I just leave it to you because I'm way over time, as I said. So this is k equals 1, 2, 3, 4, 5, 6, 7, 8 is also pretty easy. What I'm trying to say is 36, you can split it from, except with the 2, so there's a gap here, you can split it into any number of sum of squares, right, except for the 2 case. Now if I combine this result about 36 with what I got with this factor is with this thing here, and now I can easily fill out the gap from 6 to 42, namely I can find k equals 5, 6, 7, 6, 7, 8, 9, all the way to 42 by just combining these. So I just leave it to you again as an exercise because as I said, I'm way over time. And now final part. So the final one was telling us that, yes, so prove that there are infinitely many numbers and such that S of n is. So we already have shown one of them at least. So in the previous part, we showed that S of 13 is equal to 13 square minus 14, 155. So we have already showed the existence of one of them. So why infinitely many? Well, it turns out that if S of n works, then I claim S of 2n also works. So S of 2n, so I will show that this also works in answer because we already have an example. So if 13 works, then 26 also will work. 2 times 26, 52 will work. 2 times 52, 104 will work, and so on, right? So let's write down this final assertion clearly and then quickly finish with this work. So if S of n is equal to n squared minus 14, then I claim S of 2n would be equal to 2n squared minus 14, and we need to show a construction. We already know S of 13 holds, so this is true at least for one value. If it's true, then obviously it will be true for the other subsequent terms in the arithmetic progression with a difference of sorry, not an arithmetic progression, with this geometric progression with a ratio, common ratio of 2, and so 13, 26, 52, it will work for all these. And the idea is very simple. I will just apply my claim, my lemma if you will, right? So this claim, this time I will apply it for n is equal to 4n squared. So therefore, for n is equal to 4n squared, when I apply it, so 15 is less than or equal to 4n squared, which is less than or equal to 4k, and finally k is less than or equal to 4n squared minus 14. Well, when I apply it to these two, so the 4's cancel here, n squared, so k must be greater than or equal to n squared. So combining this, I realize that this I will be able to find sum of squares for this many of them. This many sum of squares between between n squared and n squared minus 14. But then I can I'm still not done, so I still need to show between 1 through n minus 1 squared, right? So to show that S of 2n is equal to 2n squared minus 14, I need to show for k is equal 1, 2, all the way to n squared minus 1, n squared plus 1, oops, and so on, n squared minus 4. What did I do here? Oh, sorry, what am I doing here? I'm high, so there's a 4 here. Sorry for that, 4n, yeah. So 4, and all the way to 4n squared minus 14. So this is our proposed S of 2n, right? So I already proved that it works using this lemma. So it's clear, right? So everybody clear that as long as you have n which is in this range, and I defined n like this, it works. So therefore all these values work. So I need to just check the validity of this one. But then I just realized that, remember that because S of n works, this one works, I already know that n squared can be written as a sum of squares, m1 squared, m sub k squared, for k between 1, 2, all the way to n squared minus 14. But then I will do this following smart move. I just realized that 4n squared is simply equal to 2m1, okay, 2n squared is equal to 2m1 squared plus plus 2mk squared. Haha. So therefore it is obvious that it will work as well for 1, 2, all the way to n squared minus 14. So I covered a bunch of other terms here. All the way to n squared minus 14 are also covered. Check, check. So therefore the only gap that I have is between n squared minus 13, n squared minus 12, all the way to n squared minus 1. So I need to just figure this gap here. This is a 12. And finally, for this one, we have the following construction. Consider the following. I can represent 4n squared by applying the following trick in the following way. 4n squared would be equal to 64 plus, luckily our n, the least n that works is 13, so that should be big enough. 4 plus 4, so we have 2 squares, a bunch of 2 squares. How many of them? Let me first write, and then I'll write the count of each one. 1. So here we have 1, obviously. Here I will split it in an intelligent way. So n squared minus 21. Here I have j of them, and here I have 20 minus 4j of them. Okay, so let's just add up these guys. So when you add these people, so you have how many terms here? So we have so n squared, so if I add all these terms, so I will get n squared minus 20, sorry, minus 1, and then plus 1, they cancel out, and then plus minus 3j. So okay, and in a similar way, I will continue expressing 4n squared in 2 more ways. 4n squared can also be expressed as 36 plus 16 plus 16 plus 4 plus 4. Obviously, I'm splitting the forms 4s in a careful way so that I make sure that it works. Okay, so how many of each one? So we have obviously 1 here, 2 here, so far we have 3 here. And here I have n squared minus 22 of them. Here I have j of them, and here I have 20 minus 4j of them. If I add these, so in total how many squares I have? N squared, again, minus 3j, but this time I have minus 2 plus 3, oh, plus 1. So that's pretty nice. And finally, so yeah, and you guys are probably already figuring what's going on. 36 plus 36 plus 4 plus up to 4, and then again I'm splitting the 4s carefully, plus 1 plus 1. Now I count them the following way. Here I have already 2 of them. Here I will have n squared minus 23 of them. Here I will have j of them, and here I will have 20 minus 4j. You can think of j as my choice variable, haha. And my choice variable in a sense in mod 3, right? So why is that? Because when I add these, I'll have again n squared, and then minus 23 minus 3 plus 2 minus 1, and then there's still a minus 3j. Minus 3j minus 1. But do you see what happened? So remember that the missing piece was n squared minus 13, n squared minus 12 all the way up to n squared minus was it 1? N squared minus, yeah, minus 1, yeah. So n squared minus 1. So these are the missing guys. So therefore what I can do is, by a careful choice of j, by splitting the the two squares in a careful way, right? In fact, let's just write it carefully. I can just pick the j's from this set in this case, 1, 2, 3, 4, and 5 if necessary. I'm not sure if the 5 will be necessary, but okay. So I can reach to any of these numbers. So that's clear, right? So every time I need one of them. So for instance, this one, I will just find the appropriate j that will work. For instance, in this case, minus 13. I cannot reach minus 13 here. I can. So by picking j equals 4 here, so I can reach it here. So this one will give me the desired result, and so on. So each one, for instance, n squared minus 12, you can easily reach it by picking j equals 4 here. N squared minus 11, you can reach it probably j equals 4 here. And then n squared minus 10, you go back to this one, j equals 3 here, and so on. So therefore, I don't think we need 5. Okay, so but you can basically reach out all the remaining ones. So therefore, we have just proved that all the it's possible to represent 4n squares by any number of squares less than or equal to 4n squared minus 14 as a sum of those squares, and that completes this lengthy proof. So hope you enjoyed the video, and looking forward to see you guys in our next lecture.